Our next speaker is Inchao Zhang. The title is Pegasus, a universal framework for scalable deep learning inference on the Dataplane. Inchao Zhang is a third-year master student at Department of Computer Science, Tsinghua University, specializing in intelligent Dataplane. Please.
Hello, everyone. My name is Inchao Zhang. I'm glad to have this opportunity to present my work, Pegasus, a universal framework for scalable deep learning inference on the Dataplane. First, let me introduce the concept of the Intelligent Dataplane, or IDP. As networks grow in scale and complexity, pushing intelligent models into the Dataplane for online traffic analysis has become a clear trend. By leveraging high-performance programmable hardware, IDP executes learning models directly in the forwarding path, enabling line-speed traffic analysis. With this approach, traffic analysis gains key advantages: line speed, intelligence, flexibility, and efficiency. Among all intelligent models, deep learning plays the central role. It originated as early as the 1950s, and since 2012, it has gradually overtaken traditional machine learning to become the dominant paradigm. In the networking domain, deep learning models also demonstrate three key advantages. First, deep learning can capture temporal patterns in data transmission. The transmission of network data inherently exhibits temporal characteristics. Models such as recurrent neural networks and one-dimensional convolution neural networks can efficiently capture these temporal features. Second, deep learning eliminates the need for feature engineering. Deep learning can extract features directly from raw packets, overcoming the difficulties of complex feature computation in the constrained Dataplane environment. Finally, deep learning enables unsupervised malicious traffic detection. In practice, developers often have only benign traffic data, while future malicious traffic is unknown and unlabeled, making unsupervised classifiers hard to apply. Unsupervised models such as autoencoders reconstruct input data, and the reconstruction error indicates whether traffic is abnormal. This allows detection of unseen attacks, including zero-day threats, even without labeled data. However, deep learning models have flexible architectures and diverse computations. Different layers require different operations, which are hard to implement on the Dataplane. This places high demand on hardware, while today's Dataplane often falls short. For example, as shown in the figure at the bottom left, operations such as multiplication, division, and exponentials are not natively supported on programmable Dataplane. This is mainly because switch Dataplane are primarily applied for high-speed packet processing using the mesh action table abstraction. As a result, they offer limited computation, pipeline stage, and on-chip storage, creating a mismatch with the computation-centric needs of deep learning. These inherent limitations restrict their ability to express learning models. To enable deep learning models on the Dataplane, two main approaches have been proposed: computation simplification and computation bypassing. As a classic example of simplification, N3IC encodes 4 features in binary form, and it replaces multiplication and addition with XOR and population count to approximate matrix multiplication, thus realizing a binary MLP on the NIC. In contrast, BOS takes a computation bypassing approach. It binarizes the input and uses the binary sequence as a lookup key, catching the full input-output mapping. In this way, BOS bypasses computations and implements a simple binary recurrent neural network purely through lookups. However, existing approach faces challenges in scalability, durability, and accuracy. For example, N3IC reduces computational complexity but still involves massive binary operations. Its 128 to 64-bit population count alone takes 14 pipeline stages, making it hard to scale on high-throughput switches. Moreover, XNOR and population count can only emulate matrix multiplications, not activations or normalization, limiting generality. Finally, full model binary causes significant information loss, leading to reduced accuracy. Computation bypassing methods faces the same three challenges. BOS caches the entire input-output mapping, but the table size grows exponentially with input size. As a result, BOS applies only to multi-time state errors with small per state inputs, which limits the generality. Finally, even with pre-stored results, BOS still requires input and output binary, reducing expressive power and hurting accuracy. To overcome these three limitations, we propose Pegasus, built on 5 tightly coupled designs. First, we transform deep learning inference operation into 3 dataplane-friendly primitives. These primitives fit naturally into the switch matrix tables. With them, the dataplane can support a wide range of deep learning models, achieving generality. Consider matrix multiplication of 8-bit inputs with unknown weights. Traditional full input-output mapping requires an enormous number of table entries, which severely limits scalability. In contrast, Pegasus adopts 3 primitives: partition, map, and sum reduce. Partition breaks a large operation into fine-grained computations on minimal input units. Map retrieves pre-computed results for each unit for lookup tables. Sum reduce agrees multiple units outputs into the final result. As shown, Pegasus computes the results of input units with their weights. Then the units are looked up in the tables to fetch the results. Finally, sum reduce aggregates length to the final output. This process is repeated until the final result. This method reduces the input each table must process, thus shrinking table size and improving scalability. In addition, Pegasus adopts field precision weights and fixed point activations rather than binary. The wider numerical range allows the model to capture more detailed information, which leads to higher prediction accuracy. Pegasus further improves scalability with fuzzy matching and primitive fusion. Fuzzy matching replaces all possible inputs with cluster centroids, storing results only for the centroids. This groups multiple inputs into one table entry. A single lookup can then cover many units, effectively reducing memory bandwidth consumption. This improves scalability. A direct decomposition of deep learning inference produces long sequence of primitives, which consume significant resources. Pegasus applies primitive fusion to merge multiple operations, reducing the total number of tables. This greatly improves scalability. The architecture of Pegasus is shown in the figure on the right. It uses primitive to abstraction to bridge computation-centric deep learning with the full-table-centric data plane. When a data flow arrives, it is logically processed by an intelligent deep learning model. This model is decomposed into a sequence of primitives. The primitives are then implemented on the mesh action tables of the programmable switch. In summary, Pegasus brings 3 key innovations. Primitive-based framework. It abstracts deep learning operations into dataplane or friendly forms, enabling diverse models to run directly on commodity switches without hardware changes. Systemized fuzzy matching. Pegasus adapts and systematizes the fuzzy matching for the dataplane using P4-compatible match rules to provide compact, approximate indexing of feature vectors. Primitive fusion. It merges multiple operations, reducing not only memory traffic but also the number of executed operations, making it well suited for resource-constrained switches. Next, let me walk you through the components of Pegasus. First, Pegasus defines 3 dataplane-oriented primitives, shown in the figure at the top left. Partition splits high-dimensional features into smaller parts. Map computes each part independently, and the sum reduce aggregates the results to produce the final output. The fuzzy matching process works as follows. We cluster the inputs with a binary tree based on feature thresholds. Each cluster is represented by a centroid, and its computed result is stored in the table. During inference, the input follows the tree until it reaches the corresponding centroid, and we return the pre-computed results. Although this method may introduce slight errors in results, the continuity of deep learning models ensures that small input changes don't cause large output variance. As a result, classification accuracy remains high, as we will later demonstrate. In summary, fuzzy matching brings out 4 key advantages. First, it saves storage resources. Second, it executes one lookup for multiple inputs, reducing the number of queries and the overhead of intermediate vectors. Third, by using fuzzy matching indices instead of the original vectors, it effectively reduces per-flow storage overhead. Finally, fuzzy matching enhances the efficiency of advanced primitive fusion, which we will cover later. Next, let me briefly introduce primitive fusion. Consider a 2-layer MLP, where each layer has 3 main operations: normalization, full connected computation, and ReLU activation. When decomposed into primitives, we use the diagram to illustrate all primitives in this 2-layer MLP. By analyzing the primitive sequence, we find the fusion pairs and explore how to merge them. First, we draw the primitive sequence corresponding to this model. Next, we perform a linear reordering. That is, swapping the order of the sum-reduced primitive and the linear mapping function. This is possible because linear mapping functions satisfy additively. So such reordering doesn't affect the model's output. Then we merge consequent mapping functions, since mathematically they are equivalent to a single larger mapping function. When simple fusion, 7 table lookups shrink to just 2, greatly improves resource utilization. The main obstacles to further fusion are the nonlinear mapping and some reduced primitives. By slightly modifying the model to remove them, we can achieve even more efficient strategies. For example, removing nonlinear mapping reduces the model to a single table lookup, but this also removes nonlinearity, limiting expressive power. Alternatively, removing sum-reduce also enables a single lookup. Here, nonlinearity is preserved, but only within units of the same table. Fortunately, fuzzy matching lets one table cover multiple inputs, which significantly boosts expressive capability. These methods can even be combined for better results. We demonstrate the power of primitives by decomposing deep learning layers. Specifically, we identify 4 categories of operations. By expressing these 4 operations with primitives, we can construct different deep learning layers. From these layers, we can further compose a wide variety of deep learning models. In addition, we design a simple syntax to lower the programming barrier. With this syntax, users only need to adjust a few parameters to implement complex deep learning models. We implemented Pegasus in P4 on a barefoot Fino 2 programmable switch connected to 2 Linux servers. For evaluation, we use packet-level macro accuracy on 3 tasks. The baselines are N3IC, a binary MLP, Leo, a decision tree model, and BOS, a binary In accuracy comparison evaluation, Pegasus outperforms state-of-the-art approach with an average accuracy improvement of up to 22%, along with up to more than 2,200 larger model size and input scale. What's more, Pegasus achieves higher accuracy with only 28 bits per flow storage, surpassing BOS and Leo. We use AUC to evaluate the capability of the unsupervised model. The unsupervised malicious traffic detection experiment shows that Pegasus enables the Dataplane to effectively handle novel and unknown attacks, including zero-day attacks, by implementing an unsupervised autoencoder model. With over 200 model scale up, Pegasus maintains acceptable resource overhead compared to BOS. Compared with full precision for software models, Pegasus shows only a slight performance drop. Compared with CPU-GPU implementations, Pegasus achieves over 3,800 and 600 higher throughput, respectively. As conclusion, Pegasus extracts deep learning models using Dataplane-friendly primitives, enabling implementation on commodity programmable switches without requiring additional complex computation resources. Experiment results demonstrate Pegasus' advantages in realizing intelligent models, address the accuracy, scalability, and generality limitation of prior IDP designs. Thanks.
Thank you, Yingchao. Do you have any questions? Okay, maybe one question for me is that you claim that you achieve like 600 times performance compared to a GPU. That's very impressive. I'm wondering, have you ever compared the Tofino switch power usage and then the GPU you use? What's the power usage comparison?
We transfer all data into the GPU memory and then run the GPU at the full power, and we compare their throughput. Yeah. Yeah,
but my question is like, do you use one single GPU and then a single Tofino? Is that right?
Yeah, four GPU. We use V100 GPU and with a Tofino 2.
Okay. Have you ever compared the power consumption between the two?
Oh, no, we not compare that.
Okay. Do you have any more questions from the audience? Okay. Thank you, Yingchao.
Okay, thank you.
Thank you.
Thank you.